This is a video of the derivation of the kinematic equations that we did in class today. I apologize that there happens to be a little bit of glare on the whiteboard at a few times during the video. Can't be helped. If you would please go to my website, and there is a PDF of these derivations written out on my website if you want to print them off and look at them so you can see things a little more clearly. But you do need to follow along as you watch this.
All right, so let's talk about the bell ringer here. Answer the following. On a dt graph, how do you find velocity? Slope. Okay, that's pretty simple. On a vt graph, how do you find acceleration? Slope. Okay, so these are things that you guys should all know by now. On a vt graph, how do you find displacement? Area. Okay, the reason these are up here is because we're going to use all of them today in one way or the other. Up until this point, we have just been dealing with the graphs, right? Yeah. And remember, what did we do the very first week of school? Algebra. We did a bunch of algebra. And then I told you that we weren't going to have to actually apply that algebra for quite some time, right? Yeah. And I said, in a few weeks, we will apply the algebra. It's been a few weeks. Okay? So what we're going to do today is I'm going to take the graphs that we have been working with and show you where the equations come from. Now, before you start freaking out and thinking, oh, I don't like algebra, it's okay. It's okay. Because, well, this is not hard. I'm not going to show you any algebra that was not taught to you in Algebra 1. Okay? And since you're all sitting in my class, I'm assuming that means you passed Algebra 1. Now, once again, just because it was taught to you doesn't mean you actually learned it, but I know it was taught to you in Algebra 1, so we're going to go through it again. And as we go through this, if you are like struggling with the algebra, you don't really know what's going on, you really need to come talk to me, because I happen to be fairly good at algebra, and I could probably help you figure it out. So you might want to make sure that you get that under your belt here. Okay? Now we're going to do this algebraically, solving all of these problems, just looking at the graphs. We're going to be talking about what we call kinematics. Okay? Kinematics is a study of motion. Specifically, study of how things move, or describing the motion of objects. Well, that's what we've been doing. Yeah, we've just been doing kinematics with graphs. Today we're going to do kinematics with equations. In a few weeks we're going to be talking about dynamics, which would be describing why things move and how things move, like what causes the motion. Today we're just going to be talking about how do we describe that motion. Okay? Everybody good? You ready? Awesome? Okay. So, we're going to start off uniform motion. A few weeks ago, I defined that term for you. Anybody remember what it was? Well, if I say uniform, what does that mean? The same. So what do you think uniform motion refers to? Same motion, or... So what would be constant? Slow. Constant velocity. So anytime you hear the phrase uniform motion, we're referring to constant velocity. Okay, the velocity is constant, means uniform motion. There are 4 kinematics equations I'm going to show you today. Only one of them will be used with constant velocity. So there's only one equation for the uniform motion situation. And in order to talk about that, I'm going to use a displacement time graph. Because on a displacement time graph, what is velocity? The slope. It was the slope. Okay, so I'm going to use a displacement time graph because I want to deal with something that has constant slope. Okay? Or constant straight line thing. So constant motion. So let's draw ourselves a displacement time graph. That looks like that. Okay? Now, pretend for a minute that this is not physics. Pretend for a moment that this is math. This is a, what type of graph?
Linear.
It's a linear graph. What's the equation for a line?
Y equals X.
That's a very specific line. Y equals mx plus b is the general equation for any line. Okay, y equals x is the general equation, or the standard equation for a very specific line where the slope is 1 and it has a y-intercept of 0. This is the general equation for a line. Y equals mx plus b. All right. On any general graph, what is, if that's the equation, y equals mx plus b, what does y represent on any graph? In this equation, y refers to, no, on this equation, y refers to, had a brain fart. It refers to the y coordinate of a point on the line, right? So that's what y is. What is the x?
The X coordinate.
The x coordinate of a point on the line. What's m? And what's b?
Y intercept.
Okay, so we've got the y coordinate, the x coordinate, the slope, and the y-intercept. Now, what is the definition of a y-intercept?
When it's what X is when Y, or what Y is when X equals 0.
Exactly. It's the value of y when x equals 0. Okay? Now, all of that is important for understanding this graph. Now, this is a displacement time graph. So, it is a straight line, so I have a linear equation. So the equation for this line is a straight line. It is a linear equation. So, on this graph, what is my y? If I'm right here, what does y refer to on that graph?
Distance.
Not distance, but
Position.
not distance, but displacement. Okay? So that's my displacement. What does the x refer to? Time. What is m? What is the slope of that line in physics terms?
Velocity.
It's the velocity. So what's the y-intercept?
Starting point.
Say that louder.
The starting point.
The starting point. Remember, the y-intercept is the value of y when x equals 0. So on this graph, it's the value of my displacement when time equals 0. Or the initial displacement. Or your starting position. Which means this is technically my final position. Or my final displacement. So everybody see that this is simply the equation of a line on a DT graph? Y equals mx plus b. This right here is kinematic equation number 1. Kinematic equation number 1. It's just the equation of a line on a DT graph. That one's pretty simple. Now, I forgot to explain to you why I'm doing what I'm doing here. I could just give you the 4 equations and then give you a bunch of problems and have you try and figure them out. Okay? I personally think that the equation makes more sense if you know where the equation came from. That's why we spent the last 3 weeks looking at graphs and how to interpret the graphs and the parts of the graphs. That's why every single day of class for the past 2 weeks, you've walked in and I've asked you, what is the slope on a distance time graph? What is the slope on a velocity time graph? How do you find displacement on a velocity time graph? I've asked you those questions or some form of those questions nearly every single day for the past 2 weeks. Okay? Because understanding where these equations come from make the equations a little easier to use. And that's what I want, is for it to be easier for you to use them. Okay? This is kinematic equation number 1. How many equations did I tell you we had for uniform motion? For uniform motion. 1, that's it. So if you have constant velocity, that's the equation. Period. Okay, it's the only equation we have for constant velocity. Now, if it's not uniform, then it's accelerated. If my velocity is not constant, then I have accelerated motion. Would I want to use a displacement time graph for these equations?
No.
Why?
Because if you look at acceleration, you need to look at the velocity.
But why? Why would I not want to use a displacement time graph for this?
Because you can't find acceleration.
Not with algebra. All right? What would a displacement time graph of accelerated motion look like?
Curve.
It's going to be a curve. All right? And unless I want to apply calculus, I don't want to deal with curves. All right? So instead of a displacement time graph for this, I'm going to use a velocity time graph. Because I don't want to have to apply calculus here. I'm doing this purely with algebra. Okay? So let's look at a velocity time graph. That looks like this. Does this graph look any different than what we just did? Is it a different graph?
Yes.
What's different about it?
Velocity times
So my y-axis is velocity, not displacement. So even though the graph looks the same, does it tell me the same thing? No, it's completely different. This is a velocity that's changing. This is an accelerated motion graph. Okay? But it still has the general equation of y equals mx plus b. That general equation still works, still applied. So, on this case, what is my y? My velocity. What is my x? Still time. What is my slope? Acceleration. Remember, velocity time graph, slope is acceleration. So what is my y-intercept?
Initial velocity.
Initial velocity, my velocity at the beginning. All right, so that would be v final, my final velocity. So again, this is simply the equation of a line. Y equals mx plus b. Final velocity equals acceleration times time plus initial velocity. It's the equation of a line on this graph. Okay? As of yet, I have not done anything super complicated. Okay? Just equations of lines. This is kinematic equation number 2. How many did I say there were?
4.
There are 4. Okay? Now, sometimes I need to know the displacement. Okay? And I'm going to refer to displacement here as delta D, or my change in position. I want you to remember that triangle. What does it mean? It means change. It's the Greek letter delta. It represents change. Pretty much every science course you'll ever take, delta represents change. And delta is always final minus initial. Never the other way around. The change is always final minus initial. What that means is, and this is the mistake that a lot of people make, your displacement or your delta D, your change, is not biggest minus smallest. If I start at 12 and end at 3, my delta D is 3 minus 12. It's not biggest minus smallest, it's final minus initial. So can you get negative answers there?
Yes.
Yes. And a negative change means it's changing negatively. So negative delta means you're changing negatively, positive delta means you're changing positively, but you have to remember it's always final minus initial. If I want to find displacement on this graph, what do I need to find?
Area.
I need to find the area. So I need to find the area of that shape. Well, the area of a trapezoid is kind of a pain in the butt. That's not really a trapezoid, but, well, it kind of is. But it'd be better to find the area like that, right? Where I have a rectangle and a triangle. So if I find the area of that rectangle, and then I want to find the area of this triangle, then what would I do? Add them together. Okay? Well, let's look at the area of the rectangle first. How do you find area of a rectangle?
Side 1.
Base times height, length times width, side 1 times side 2, however you want to look at it. What is this?
Base. Time.
It's my time, right? Specifically, that would be my change in time. What is this right here?
Change in velocity.
What is that right there?
Initial velocity.
That's my initial velocity, right? Because it's my y-intercept. That's my initial velocity. So the area of this whole shape is my initial velocity times my time. That's the area of that rectangle. Did you see that? It's your initial velocity times the time. That's the length and the width of this rectangle. So now I need to find the area of that triangle. How do you find the area of a triangle? Base times height divided by 2. Okay? And just because I want things to come out a certain way, I'm going to write it as height times base divided by 2, which is not any different. But what's the height? Well, let's make it easier. What's the base on this? My base is my change in time still. All right? Okay? What is my height of this triangle?
Change of velocity.
Initial velocity or change in displacement.
Not displacements, but change in velocities. Because this right here is my final velocity. If this is my initial velocity, then this is my final minus my initial, or my change in velocity. Does that make sense? So that means the area there is my change in velocity times my time divided by 2. Or my height times my base divided by 2. It's the area of a triangle. Everybody see that? Now, I want you to look at Kinematics equation number 2 for a second. And I'm going to write that as VF minus VI equals AT. All I did was I took this and subtracted it to the other side with algebra. So this is the same as this equation, right? Everybody see that? Now, what does that equal? A times T equals VF minus VI, right? Everybody see that? So can I take that and plug it in right there?
Yeah.
Yeah, because VF minus VI equals A times T. So I'm going to replace this VF minus VI with A times T, but then I still have that T there. What is T times T? T squared. So, my area is my displacement, right? My area is my displacement. And the area is VI times T, or the area of this rectangle, plus 1/2 AT squared, the area of that triangle. That's what the area of that triangle is 1/2 AT squared. Okay? This is kinematic equation number 3. Now, once again, all we have done is applied physics terms to equations of lines. And I found the area. Okay? You have already done this on that linear motion worksheet where you drew the graphs and you found the area and you found the slope. You were using these equations even though you didn't realize that's what you were doing. Make sense? This is where these equations come from the graphs. Okay? I wanted you to see where they came from so that the equations make more sense. Because otherwise, they're just equations. They don't really have any meaning. Now, hopefully you see that this has meaning. It's the area of that graph. This has meaning. It's the area of that triangle. Okay? Now, how many kinematics equations have I given you so far? 3. How many did I tell you there were? 4. Now, I'm going to take a slight little break for a second and explain something to you. The 4th equation, I could just give to you. And usually that's what I do. I just give you the equation because the derivation of it's a bit of a pain in the butt. But I will also find that when I just give the equation, nobody ever wants to use it because they think that that equation looks hard. Okay? And so I'm not going to do that today. What I want to do instead is show you where that equation comes from. Okay? So, if you are one of those people who says you're not very good at algebra, now would be a really, really, really good time for you to be paying attention to what I'm doing. Because I'm going to do some algebra gymnastics. Okay? And the best way to get better at algebra is to, see it done correctly and then practice it yourself. So you watch me do it, you write it down, and hopefully you understand what I'm doing because I'm going to explain each step while I do it. And hopefully you get better at the algebra instead of just saying, well, I'm not good at algebra, so I'm going to fail physics. That's not a good attitude to have. Instead of saying, I'm not good at algebra, I'm going to fail physics, let's say, let's get better at algebra so physics is easy. Okay? You with me? Now, I'm going to show you how we get that equation, but before we do, I want you to ask yourself, of the 3 equations I've given you so far, what is in all 3 of those equations?
Velocity.
What else? Time. Okay? See, the thing is in the first equation, yes, there's velocity, but there's only one velocity. Right? In the other 2 equations, you have VF and VI. But time is in all 3 equations. Will there be instances where you don't know how much time passed? Yeah. If you're trying to find out how fast something is going and you don't know how much time has passed, can you use any of those equations that I've given you? No. Everybody see the problem? Anybody ever wonder how 3 hours after a car wreck, the police investigators can tell you how fast the car was driving? Well, how do they know? No one was there to measure the time. You don't have to know how much time passed to be able to figure it out. Okay? And it's because of this last equation. So first, I'm going to start off with the 2 kinematics equations we just had. Kinematic 2 and kinematic 3. Now, in algebra, if I gave you two equations with different variables like this, there's a couple of different ways to solve it, but typically what would be one of the easier ways to do it would be to solve both the equations for one variable and set them equal to each other. Like if I gave you an equation with x and y and another equation with x and y, and you solve both equations for x, then if they both equal x, you can set them equal to each other and solve for y. Right? Now, I don't want to do that with this. But you have two equations, and we just said we want to get rid of t. So if I solve it for t and then equal them to each other, then I don't have t anymore. What kind of equation is that? Starts with a Q, ends with a hell on earth. Quadratic. All right. Most of you are like, the only way to solve for t right there is to use the quadratic equation, negative b plus minus square root of b squared minus 4ac all over 2a. You guys remember that from Algebra 1? You're like, I remember the stupid song that goes to the Pop Goes the Weasel thing that I really don't want to sing. Jacob wants to sing it. Okay, so you don't have to use the quadratic equation. We could, but we don't want to. So instead what I'm going to do is I'm going to take this equation here and I'm going to solve it for t. To solve this equation for t, what do I need to do? I want to have t equals. What do I do? I subtract vi first. I got to move the term that doesn't have t in it. So I subtract vi first. Then what do I do? Now I divide by a, which gives me vf minus vi divided by a equals t. Now we're going to do some substitution. Because if this equals t, then I can take that term right there and plug it in for t there, and I can plug it in for t there. Okay? So now I have delta d equals vi times t, because t equals this, plus 1/2 a times t squared. Okay? Now, again, said we're going to do some algebra gymnastics. So, when I have something outside the parentheses squared, that means I square everything inside the parentheses. So I'm going to distribute that square. Like that. Okay? And I'm also going to distribute my VI. So now I have VI times VF minus VI squared, because VI times VI is VI squared. All of that over A. So I distributed by VI, so multiplied it by both things. I distributed my squared. Now, if I'm multiplying these together, what's going to happen to these A's? I have A in the numerator, A in the denominator. What's going to happen? They're going to cancel out. Do they cancel out completely? Why not?
It's a square.
Because this one's squared. So that A, the one in the numerator, goes away, and one of those goes away. Everybody see that? So now I have, and if this is 1 over 2, that means that 2 is in the denominator, right? So that means this is VF minus VI squared over 2A. That's what all of that becomes this. Now I have two fractions that are being added. Can I add those two fractions? What do I need in order to add them? You need a common denominator. What would the common denominator be? 2. Or 2a, yeah. So I want to have this have a denominator of 2a. How do I do that? Multiply both sides, or top and bottom, by 2. All right? Don't just multiply by 2. You have to multiply the numerator and the denominator by 2. So you're not changing the value, because 2 divided by 2 is 1. Okay? So when I multiply the top by 2, that gives me 2 times VI VF. But I also have to multiply this by 2. So that's 2 VI squared. And then I still have my VF minus VI over here, quantity squared. And all of it is over 2a. Because once I get a common denominator, I can add them together. And I realize that you're probably sitting here thinking, this is getting more complicated as we go. It's about to get a whole lot easier, or a whole lot more simplified. Okay? If this right here, VF minus VI, is squared, does that mean I'm going to have VF squared minus VI squared? No. Because let's think algebra for a second. If I just gave you a minus b squared, that's the same as a minus b times a minus b. So in order to multiply out this polynomial, I have to do the FOIL technique. First, outside, inside, last. You guys remember that? Okay? So that becomes a squared minus ab plus b squared. What can I do with these two ab's?
Negative 2ab.
Can I combine them? So I have a squared minus 2ab plus b squared. That's what you get whenever you multiply out, or when you square that polynomial. Okay? That's called a perfect square binomial. Does this right here look like this would? I have something minus something squared, right? So I'm going to do the same thing to this. Okay? So that term right there becomes VF squared minus 2VIVF plus VI squared. That's what this becomes when you factor it out, when you multiply it out like that. When you FOIL it, you get this. Okay? Now, what does all of this still equal? It still equals delta D. I never took that away. All right? So I want to get rid of this in the denominator. So what do? How do I move this to the numerator? Multiply the entire thing by 2a, which is going to give me 2a delta D equals all of that. Okay? I'll go ahead and write it out. We have 2vi vf minus 2vi squared plus vf squared minus 2vi vf plus vi squared. And some of you are sitting there thinking, you just said this was going to get easier. That doesn't look easier. Yeah, it does. It's a whole lot easier. What's 2vi vf minus 2vi vf? They cancel out. I have negative 2vi squared and a positive 1vi squared. What's minus 2 plus 1? So that goes away, and I'm left with vi squared negative plus vf squared. Okay? Now, that's why I'm recording this. You can watch this again later if you want. All right? Now, I don't want to have a negative here, so how do I move this negative? How do I move the whole thing? If it's minus, I add it. So if I add it to both sides, that gives me 2a delta d plus vi squared equals vf squared. And if I flip it around to where the thing that we have by itself is on the left, because that's the way you're used to seeing equations, that's kinematic equation number 4. Okay? Now again, I told you up front that that was going to be a very complicated derivation, and you don't necessarily have to know how to do that. But when I just show people this equation, they start freaking out because there's 2 things that are squared in there. Would you rather use this equation or this one? Yeah, you'd rather use this one, right? I show you the whole thing so you can appreciate this equation. Make sense? So this is kinematic 4. Now, because I am a super science geek and a comic book nerd, I have special names that I have given these equations. Okay? And I will use them periodically, so I'm going to go ahead and tell you what they are because I want you to recognize what they are. First off, and most of you are going to disagree with me on this because, well, you're your generation and I'm my generation. But we can have a discussion about that later. This equation right here can be used on almost every single problem I give you. It can be used to solve so many things. I can solve for displacement, I can solve for velocity, I can solve for acceleration. It can do it all. It has many, many superpowers, not just one. Superman. All right? It's the one that does it all. It's the best. It's the first go-to thing. Okay? But there are certain situations that that one cannot be used, like we just discussed. All right, so this is what I refer to as the Superman equation. If you ever hear me say use the Superman equation, that's what I'm referring to, because Superman can do it all, with the exception of one thing. When can Superman not do what Superman needs to do? When there's kryptonite. All right? This equation's kryptonite is when you don't know time. If you don't know time, you can't solve this equation. So, not having time is kryptonite. And when the Justice League has a problem and kryptonite is involved, we can't send Superman, so we send in Batman. Elegant, sophisticated, overly complex, but doesn't really do a whole lot. Batman. Okay? Spoiled little baby with a whole lot of money. Take away his toys, can't do squat. Okay? Batman. Elegant equation, but really not that useful. Now, the third equation is, well, you have Batman, you have Superman, and if Batman and Superman are there, you don't really need Robin. He's just kind of superfluous. If you got Batman, Superman, Robin's kind of useless. There are times that he's, he can get the job done, but if you got Batman and Superman, you don't need Robin. Kinematic equation number 1 that I gave you, constant velocity equation. In most situations where we do not have constant velocity, that equation is absolutely useless, and so he's Aquaman. Because Aquaman is pointless. All right? So, why do you need to talk to dolphins? Really? Okay. Okay, we'll have an argument about, we can have an argument about comic book characters later. Hey, these are the 4 kinematic equations. Tomorrow I'm going to show you how to use these equations to solve problems. And then you're going to get practice. So I strongly suggest you are here tomorrow and you're paying attention.